quiet archive record. Tonight, we drift into a place where silence carries the story. There is nowhere to go, nothing to hold on to, only a slow pull into the void. In this episode, we look at distance as something a human body can actually cover within one lifetime, starting with walking and sailing, and ending with rockets and the strange math of near light speed. We compare how far a person could go if they never stopped moving, and how far they could go if they travel the way real people do, with sleep, repairs, money, borders, and weather. We put numbers on everyday travel and on extreme records, like long ocean voyages, non-stop flights, and missions beyond Earth. We also explain the hard limits, like energy, fuel, radiation, and time, and the softer limits, like politics and psychology. By the end, the question is not only how far a person could move through space, but how far they could move through history as travel tech changes during their years. Tonight we explore how far we could travel in a human lifetime. A lifetime sounds long until you try to spend it as distance. Imagine a clock that starts the moment you are old enough to travel alone and stops the moment your body can no longer handle long days. For many people, that window might be 50 years, maybe 60 if luck and health hold. Now imagine a second clock that is harsher. It counts only the hours you are moving, not the hours you are waiting, eating, fixing a vehicle, finding money, or sleeping. Those two clocks create two very different answers. If you ask how far a human could travel in a lifetime in the most extreme way, you would push the second clock. You would try to be in motion almost all the time, even if it means changing vehicles and crews, living on the edge of what the body can stand. If you ask how far a human could travel in a lifetime in a realistic way, you would use the first clock. You would include the pauses that are part of being human. The simplest form of travel is walking. Walking is old enough that it shaped our bones. A typical adult walks at about 3 miles per hour on flat ground, which is around 5 kilometers per hour. That is a speed that does not sound like much until you multiply it by time. If someone walked for 1 hour, they might cover 3 miles. If they walked for 8 hours, that could be 24 miles. That is close to 40 kilometers. A fit person on a long trail can do that for many days, though not forever. Real long-distance hikers often average 15 to 25 miles per day, depending on terrain and load. Now push the extreme idea. Suppose a person could walk 10 hours a day at 3 miles per hour. That is 30 miles per day. Over a year, that is about 10,950 miles, more than 17,000 kilometers. Over 50 years, it would be more than 500,000 miles, close to 800,000 kilometers. That is roughly 20 times around Earth at the equator. But nobody walks like that for 50 years. Bodies break, feet split, knees wear. Weather blocks the path. Borders do not always open. And most important, there are not roads that let you walk in a straight line without interruptions. The world is water and mountains and private land. When humans did spread across continents on foot, it took many generations, not one lifetime. That is a key lesson. If you want to know what one person can do, you must respect the limits of one body. Still, walking gives a baseline. It tells you that the human body, without machines, can turn food into motion and cover serious distance in a year. If you had to, you could cross a continent. Now add the oldest upgrade, the domesticated animal. A horse can walk at around 4 miles per hour and trot faster, and it can carry weight. For long travel, riders often switch horses. In the age of mail relays, a message could travel very far because fresh horses waited along the route. The rider did not need to rest as much because the animal took some strain, but the human still needed sleep. With relays, a team could cover 100 miles in a day, sometimes more. Over a year, that kind of travel could circle Earth. Over a lifetime, if there were money and a purpose, a person could cover millions of miles, but it would not be one continuous journey. It would be a life of travel as a job. The next big change is the wheel. With carts and then bicycles, human power can be turned into far more distance per calorie. A bicycle is one of the most efficient machines ever made. At a steady pace, a cyclist can go 15 miles per hour, about 24 kilometers per hour, on flat roads. If you ride for 4 hours, you can cover 60 miles. In a long day, you could cover 100 miles. Some cyclists do far more. Records for endurance rides show that trained people can ride 200 to 300 miles in a day, sometimes more. But it is hard, and it is not a daily thing. Let us build a rough picture. Suppose a person rides 80 miles per day, 5 days a week, and rests 2 days. That is 400 miles per week. Over 52 weeks, that is about 20,800 miles. Over 10 years, it is 200,000 miles. Over 50 years, it is 1 million miles. That is more than 40 times around Earth. This is still extreme, but it is closer to human reality than non-stop walking. There are people who have spent years cycling around the world. They are not moving every day, but they do cover huge distances. Now we step into engines. An engine is time made dense. It lets you spend stored energy faster than muscles can. A car on a highway can move at 60 miles per hour, around 100 kilometers per hour. At that speed, the planet feels smaller. If you drove 8 hours per day at 60 miles per hour, that is 480 miles in a day. Over a year, it is 175,000 miles. Over 10 years, 1.7 million. Over 50 years, 8.7 million miles. Yet again, nobody drives like that for 50 years. But a long-haul truck driver might do 100,000 miles in a year for many years. Taxi drivers can also rack up huge numbers. Some people have cars that cross 1 million miles during their lifetime of ownership. The machine can do it if maintained. So the question starts to split. Are we talking about what a human body could personally do, or what a human could do by commanding machines and paying for fuel and maintenance? In most modern travel, the body is not doing the work. The body is paying, waiting, and choosing. But it still matters because the body has to survive the pace. A person can sit in a car for many hours, but the mind grows tired and the risk of mistakes rises. If you never stop, you crash. A train can be even more efficient. High-speed trains can run at 200 miles per hour. In places where the network exists, you can cross a country in a day. In the 19th century, trains rewired the sense of time. Cities that were once days apart became hours apart. At sea, ships gave the first true global travel. Sailing ships were slow, but they could carry supplies. A typical sailing ship might average 5 to 8 knots, about 6 to 9 miles per hour, depending on winds. Steamships, later, became more reliable. If you want to measure how far someone could travel by ship in a lifetime, you could imagine a sailor who spends years at sea. A ship can cross the Atlantic in 2 weeks with steam, longer with sail. A sailor could cross oceans many times. Over a career, the miles add up. But here is the difference. On a ship, you are moving even while you sleep. Your personal clock is not the same as the motion clock. This is a trick of the question. When you travel with a vehicle that runs without you, your human time is not spent on the movement. Your life can contain far more distance. This becomes even more dramatic with air travel. A modern jet cruises at around 500 to 600 miles per hour. In 8 hours, you can cross an ocean. In 16, you can cross half the world. If a person took a long-haul flight every week, they could rack up huge miles. A frequent business traveler can fly 100,000 miles a year. Some fly 200,000. There are people with several million lifetime flight miles. 1 million miles is a lot, but it is still only 40 times around Earth. The number sounds giant, but the planet is big. Now push a strange thought experiment. What if a person could stay on a plane almost all the time? Like a crew member who never goes home. Planes need maintenance. Crews need rest. But imagine rotating crews, and imagine one passenger who always boards the next flight. They could fly perhaps 2,000 miles in a day on average if connections are smooth, more if non-stop routes are used. 2,000 miles per day is 730,000 miles per year. In 10 years, it is 7.3 million. In 50 years, it is 36 million miles. That is more than 1,400 times around Earth. Yet this is fantasy. The body would not handle it. The mind would not handle it. The immune system would not handle it. And money would run out, so we need to decide what counts. One way to anchor the question is to imagine a person with a normal life. They work, they take vacations, they maybe move once or twice. They travel for family. They might do one big trip every year or two. For many people in rich countries today, lifetime travel might be a few 100,000 miles total, including commuting. For people in poorer regions, it might be far less. For a person in the past, it might be a few 100 miles. The greatest distance a human could travel is not only a matter of technology, it is also a matter of birth year. If you were born in 1700, you could not fly. If you were born in 1900, you might fly late in life. If you were born in 2000, you might fly often. The lifetime window sits inside history. Now we widen the lens beyond Earth. Human travel has 2 big walls. The first is the speed limit of ordinary life. The second is the speed limit of physics. The closer you move to the second wall, the stranger time becomes. To leave Earth, you need a rocket. A rocket is not like a car or a plane. It is a machine that throws mass away at high speed to push itself forward. That means it carries its own reaction mass, its propellant. This makes rockets expensive and hard. So far, only a few 100 people have traveled to space. Most of those trips lasted days or weeks. A smaller group has spent months. A few have spent more than a year in total. Distance in space travel is a strange measure. When an astronaut goes to the International Space Station, they travel about 250 miles up, which seems small. But then they orbit Earth at about 17,500 miles per hour. Every 90 minutes, they go around the planet. In a day, they might circle Earth 16 times. In a week, more than 100 times. If you add up the miles, An astronaut who spends 6 months in orbit travels tens of millions of miles relative to Earth. This is distance without getting farther away. It is like running on a treadmill that wraps around the world. If the question is strictly about distance traveled through space, not about displacement from home, then astronauts already win. A person could travel more miles in 1 year in orbit than most people travel in a lifetime on Earth. But if the question is about how far away you could go, then we care about displacement. In that sense, the farthest humans have gone is to the moon. The moon is about 239,000 miles away. The Apollo missions took about 3 days to get there. The astronauts were away from Earth for about a week. So, in a human lifetime, could you go farther than the moon? With today's tech, yes, in theory, but not in practice for most people. Mars is much farther. The distance changes because the planets move. At closest, Mars is about 34 million miles away. At farthest, about 250 million. A trip to Mars with current chemical rockets would take months. Some mission plans suggest 6 to 9 months one way. That means a round trip might take 2 to 3 years, when you include waiting for the planets to align for the return. In one lifetime, you could do that once, maybe twice, if you could survive, and if the mission existed. Beyond Mars, the outer planets are far. Jupiter is hundreds of millions of miles away. Saturn is nearly 1 billion at times. Uranus and Neptune are farther still. Robotic probes take years to get there. A human lifetime is short compared to those distances when you use current propulsion. So the question shifts again. What if the future brings faster rockets? There are concepts like nuclear thermal rockets, where a reactor heats hydrogen and throws it out for thrust. There are nuclear electric systems that use reactors to power ion engines for long, steady acceleration. There are ideas like fusion rockets, where the energy density is much higher. There are also light sails, pushed by sunlight or lasers. The key idea is that if you can accelerate for a long time, you can reach high speed, even without a giant engine burn. In space, there is no air drag. If you keep pushing, you keep speeding up. Suppose you had a ship that could accelerate at 1 meter per second, about 1/10 of Earth gravity. That is a push you could perhaps live with for long periods if the ship is designed well. In 1 day, at that acceleration, you would reach a speed of about 86,400 meters per second, around 193,000 miles per hour. That is already faster than any spacecraft humans have ridden. After 10 days, you would reach nearly 2 million miles per hour. After 100 days, you approach a significant fraction of the speed of light. But this is where physics bites. To keep accelerating, you need energy, and you need reaction mass unless you have some way to push without throwing mass away. Also, at high speeds, interstellar dust becomes dangerous. A grain of sand becomes a bullet. Still, as a thought experiment, steady acceleration is powerful. If you accelerate halfway to your destination, and then flip and decelerate halfway, you can travel to far places in surprisingly short ship time. This leads to the most extreme version of the question. How far could a human travel in a lifetime if they had a ship that could go close to the speed of light? The nearest star system, Alpha Centauri, is about 4.3 light years away. A light year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. In 1 year, that is about 5.9 trillion miles. So Alpha Centauri is roughly 25 trillion miles away. At normal rocket speeds, that is impossible. At 1% of light speed, it would take 430 years. At 10%, 43 years, which is close to a lifetime, but still long. At 50%, less than 9 years. Now time dilation enters. If you travel close to the speed of light, your time slows relative to people at home. To you, the trip can be shorter. This is not science fiction. It is measured. Particles in accelerators live longer because their clocks run slow. GPS satellites must correct for relativity because time runs differently in orbit. If a person could travel at 99.9% of light speed, they could cross the galaxy within their own lifetime, while many thousands of years pass outside. But the energy required, staggering. The kinetic energy grows without bound as you approach light speed. So we need to separate physical possibility from engineering reality. A human lifetime is also a biological limit. Even if you can go far, can you stay alive? Space is filled with radiation. Cosmic rays can damage DNA. Microgravity weakens bones and muscles. Isolation can strain the mind. A ship would need shielding, artificial gravity, food, water, and repair systems. This is why near-term, human deep space travel is likely limited. It is not only about propulsion, it is about making a small world that can carry you. There is another trick. You do not have to move your body to travel far. You can send information. You can watch remote cameras. You can control robots. But the question here is physical travel. So we return to bodies and vehicles. Let us go back down to Earth for a moment and build more grounded comparisons. When people think about distance, they often imagine a straight line on a map. But travel is more often loops and routes. Commuting is a loop. Delivery routes are loops. Even a world trip is often a set of loops between hubs. So a lifetime travel total can be high, even if you never go far from home. A person who commutes 20 miles each way travels 40 miles per day. Over 250 work days, that is 10,000 miles per year. Over 40 years, it is 400,000 miles. Add errands and trips, and the number grows. This is why many people have lifetime totals that rival the distance to the moon without ever leaving Earth. But if you want far away, you need one of two things. You need speed, or you need time without stopping. On Earth, the fastest way to move is by plane. The fastest planned passenger service today reaches about 600 miles per hour. There was the Concorde, which could cruise at around 1,300 miles per hour, but it is retired. There are military jets and rockets that can go much faster, but they are not used for regular travel. So if we imagine an extreme but still human scenario, maybe someone becomes a test pilot or an astronaut or a crew member on a high-speed aircraft, and they spend decades in that world. But a human lifetime is still only so many years. Even if you flew at 1,000 miles per hour for 8 hours per day for 50 years, you would cover 1,000 times 8 times 365 times 50 miles. That is about 146 million miles. 146 million miles is about 1.5 times the distance from Earth to the Sun. This is a striking number. It suggests that with a lifetime of high-speed travel, you could, in total distance, match the scale of the inner solar system. But again, you would not get away from Earth by that much. You would just be moving around within the atmosphere. To truly get far from Earth, you need a spacecraft, and you need the will to send it. In the next part of this story, we will look at what sets the limits in each domain, from the limits of legs to the limits of fuel to the limits of time itself. We will also look at real cases of people who have traveled far, and why their stories reveal the hidden costs behind any large number. The hidden costs begin with the body. Even the simplest distance, walking, is a negotiation with skin and joints. Feet are not wheels. They are living tissue. Each step is a small impact. Over a day of 20 miles, you might take 40,000 steps. Over a year of that, it is more than 14 million. A lifetime of hard walking would grind down almost any person unless their pace is broken by long rests. This is why record attempts in walking and running are often short in the scale of years. They are impressive, but they are also warnings. The fastest way to break a human is to demand the same hard day without end. Long-distance runners sometimes talk about the difference between training pain and injury pain. In normal life, that difference keeps you alive. If you ignore it, you can run through damage until it becomes permanent. So, when we imagine a person who walks or cycles around the world multiple times, we should picture the rest days as part of the story, not a flaw in the math. The same applies to machines. Cars break, tires wear, engines overheat, ships need dry docks, planes need inspections. The faster and more complex the machine, the more it depends on support. In other words, distance is not only a function of speed and time, it is also a function of a supply chain. A person on a bicycle can repair a flat tire with a simple kit. A person on a jet cannot fix an engine in a hotel room. They need a whole system. That system is invisible to most passengers, but it is the reason high-speed travel exists. It also suggests a way to answer the lifetime travel question with honesty. We can break it into tiers. The first tier is self-powered travel. That is walking and cycling. The second tier is personal vehicle travel. That is cars, motorcycles, small boats. The third tier is industrial travel. That is trains, ships, airlines. The fourth tier is space travel. And the fifth tier is speculative travel, where the physics is real, but the engineering is not yet. In each tier, the maximum lifetime travel depends on what kind of life you allow. If you allow an extreme life, where travel is the only purpose, the totals can be enormous, especially in tiers where the vehicle moves while you rest. If you require a more normal life, with home, relationships, work that is not travel, then the totals fall. Now let us look at the most common way people actually accumulate distance. It is not grand expeditions. It is routine. Modern cities spread out. People live far from work. They shop at big stores in other neighborhoods. Children are driven to school or sports. The miles stack up with no drama. A commuter who drives 30 miles each way covers 60 miles a day. In a year, that can be 15,000 miles. Over 40 years of working life, it is 600,000 miles. That is already farther than the distance to the moon. Add road trips, add vacations, add visits to family, add moving to a new city. It is easy for a modern life to include 1 million miles of movement without a single heroic trip. The same can happen with flying. A person who flies once a month for work might take 12 round trips a year. If each trip is 1,000 miles each way, that is 24,000 miles per year. Over 30 years, it is 720,000 miles. A person who becomes a pilot or flight attendant can do far more. Some airline crew members log tens of thousands of flight hours. At 500 miles per hour, 10,000 hours is 5 million miles. There are also elite travelers who live the air. Some business leaders and diplomats and consultants have careers built on constant movement. Their bodies learn the rhythm of airports. Their sleep is in fragments. Their sense of place becomes thin. If you have ever met someone like that, you notice something. Their stories are not about distance. They are about time. They talk about delays, jet lag, missed connections, strange meals, and the feeling of waking up and not knowing where you are for a moment. That is a human reminder. Even when machines make distance easy, the mind still experiences travel as disruption. Now consider travel by sea. A modern container ship can cruise around 20 knots, around 23 miles per hour. That is slower than a car, but it does not stop. It can run day and night. A sailor on such a ship might cross an ocean in 10 to 14 days. Over a career, they might circle the world many times. In older ages, sailors often spent years away from home. A whaling ship could stay at sea for years, moving across wide areas in search of animals. The miles travelled were huge, but the reason for movement was not the distance itself. It was work. This pattern repeats across history. The people who travelled far were often doing a job that required it, or they were forced. Merchants travelled with caravans. Soldiers marched. Enslaved people were transported across oceans. Pilgrims walked long roads. Nomads followed herds. If you want the maximum lifetime travel in the past, you might look at these groups. But the past also shows the strongest limit: risk. When travel is slow and dangerous, long distances are rare. It is not because humans cannot move. It is because the cost is high and the chance of not returning is high. A person in medieval Europe might never go more than 30 miles from their birthplace, not because they lacked curiosity, but because leaving the local network was like stepping off a cliff. Now, in the modern world, the risk is lower, and so distance becomes a background feature of life. That suggests a different way to measure how far a human could travel. We could ask how far the world could carry a person. In other words, if you had unlimited money and the ability to buy tickets and maintenance, could you keep moving for decades? In that case, the limit is not the body as much as it is the system. Airlines have schedules. Planes need airports. Roads end. Borders close. Weather cancels flights. Wars block routes. A person could plan to circle Earth every day, but the world does not always cooperate. So even in the richest scenario, the maximum is constrained by the shape of human infrastructure. Now let us step into the atmosphere and then past it. The boundary between air travel and space travel is not only altitude, it is energy. To stay in the air, a plane must overcome gravity and drag. It does that with wings and engines. The fuel is carried, but it does not have to carry oxygen because the air provides it. A rocket cannot use air in the same way. At high altitude, there is no oxygen to burn. A rocket must carry both fuel and oxidizer. That makes it heavy. It must lift its own fuel. This is why space travel is expensive. Even reaching low Earth orbit takes enormous energy. The orbital speed is about 7.8 kilometers per second, about 17,500 miles per hour. That is the speed you need, so that as you fall around Earth, you keep missing the ground. If you do the math, the kinetic energy of a person moving at that speed is huge. For a 100-kilogram astronaut in suit, It is about 3 billion joules, not counting the rocket and the fuel. That is roughly the energy in about 70 kilograms of gasoline. But rockets are inefficient, and they must also lift their tanks and engines. Still, this gives a sense. Space travel is not magical. It is energy intensive. Now think about lifetime travel in orbit. If an astronaut spends 1 year on a space station, orbiting every 90 minutes, they make about 5,800 orbits in that year. Each orbit is about 25,000 miles around. Multiply that, and you get more than 140 million miles traveled. That is about the same as the earlier thought experiment of flying at 1,000 miles per hour for decades, but the astronaut did it in 1 year. This is why, if you define travel as total path length through space, then the easiest way to maximize it is to go to orbit and stay there. A human lifetime could include multiple long stays in orbit. Some astronauts have spent over a year in space across multiple missions. A future station or a lunar base might allow more. In that scenario, a person could accumulate billions of miles traveled without ever getting far from Earth. But if you define travel as how far you can get from Earth, then we are back to displacement. The farthest displacement of a human from Earth is still on the Apollo missions. They went about 240,000 miles away. Could a human lifetime include a trip to Mars? Yes, if the missions become routine and if the person is selected. But could a human lifetime include a trip to Jupiter? With current propulsion, a human could in theory go, but it would likely take several years and expose them to strong radiation near Jupiter. There is also the issue of gravity wells. To go outward, you must climb away from the sun. You can use gravity assists, stealing a little energy from planets by flying past them, but that requires long times and precise navigation. Robotic probes have done this. Voyager 1 and Voyager 2 used gravity assists to reach the outer solar system and then head toward interstellar space. They travel at about 10 to 11 miles per second relative to the sun. At that speed, they cover about 600 million miles per year. In a human lifetime of 80 years, that is 48 billion miles. 48 billion miles sounds like it should be enough to reach another star. But the nearest star is more than 25 trillion miles away. That is 500 times farther. At Voyager speed, it would take tens of thousands of years. This is the true scale of interstellar space. It is not just far, it is empty far. So for a human to travel to another star within their lifetime, either the ship must go much faster, or the human must find a way to live much longer, or the ship must carry generations. Generation ships are another classic idea. If you cannot go fast, you bring a small society and let the trip take many lifetimes. The people who arrive are not the people who left. But the question here is one human lifetime, one body. So if we want to keep that, we need high speed. High speed brings us to relativity. In everyday life, relativity seems like a trick. You can ignore it. But at speeds close to light speed, it becomes the center of the story. Light speed is about 300,000 kilometers per second. Nothing with mass can reach it. As you approach it, the energy needed to add more speed rises steeply. The rule is simple to say and hard to live with. The faster you go, the more your time slows relative to those who stay behind. This creates a strange possibility. A traveler can cross huge distances within their own lifetime if they travel close enough to light speed. But when they return, everyone they knew is long gone. This is sometimes called the twin paradox. One twin stays on Earth. The other travels fast and comes back younger. It is not a paradox in the physics. The traveler changes frames and feels acceleration, while the stay-at-home twin does not. The point for our question is this. If you allow near light speed travel, the maximum distance in one human lifetime can be enormous. Not because the universe becomes smaller, but because the traveler's time becomes slower. In the traveler's own frame, their lifetime clock is the one that matters. Suppose a person has a ship that can reach 99% of light speed. At that speed, time dilation is about 7. That means that for every year, the traveler experiences about 7 years pass for those at rest. At 99.9%, the factor is about 22. At 99.99%, it is about 70. At 99.999%, it is about 220. You can see how quickly it grows. If a traveler could maintain a speed where the dilation factor is 100, then in 1 year of their life, they could travel about 1 light year as measured in their frame. But 100 years would pass outside. In a lifetime of, say, 60 years of adult travel, they could cover 60 light years in their own time, but 6,000 years would pass for Earth. That would be enough to reach many nearby stars. If the factor were 1,000, a lifetime could cross thousands of light years, and Earth would advance by tens of thousands of years. At those scales, you are no longer traveling to visit. You are traveling to leave. But we are far from being able to do that. The energy needed is the hard wall. The kinetic energy of a ship scales with the relativistic gamma factor, the same factor that describes time dilation. For a 1-ton ship to reach 99% of light speed, you need energy comparable to thousands of megatons of TNT. For a ship heavy enough to carry a human and shielding and life support, it becomes absurd by current standards. Then there is the issue of acceleration. If you accelerate too hard, you crush the body. If you accelerate too little, the trip takes too long in your own time. So any realistic near-light speed ship in stories uses something like 1 gravity acceleration, the same as standing on Earth. That is comfortable, and it also gives a simple travel profile. Accelerate at 1g for half the trip, then flip and decelerate at 1g. With 1g, you can reach a significant fraction of light speed in about 1 year. That means that a ship could reach distant stars in a few years of ship time, thanks to time dilation, while many years pass outside. But again, the engineering is beyond us. So, where does that leave the original question? If we keep to what humans can do today, and we measure displacement, the farthest a human could travel in a lifetime is likely somewhere in the inner solar system. Perhaps Mars, perhaps an asteroid, perhaps the moon many times. If we measure total miles traveled, then a person who spends years in orbit can exceed almost any Earth-based traveler. If we allow speculative propulsion, then the distance can expand to the stars. But it comes with a price in energy and in separation from the rest of humanity. The rest of this narrative will move between these meanings of travel. We will treat them as separate answers, because they are. And along the way, we will keep returning to a simple idea. Distance only matters when you can survive the path. Now, to make the question concrete, it helps to picture a map and a calendar at the same time. Earth is about 24,900 miles around at the equator. A bit less if you go around a latitude line closer to the poles. Most world travel routes are not perfect circles, but the number gives a scale. If you could go around Earth once, you would have done something most humans in history never did. If you could do it 10 times, you would have seen the planet change. If you could do it 100 times, you would have made travel your identity. So how many circles can one lifetime hold? On foot, a circle around Earth would take years, and only if you include boats where land ends. The fastest known circumnavigations on foot take more than a year and require planning and support. They are not a wandering stroll. They are an organized campaign. On a bicycle, a circle can be done in months. Many people have cycled around the world in a year or two with long stops. If you remove the stops, it can be faster. In a car, you could circle Earth in weeks if roads existed everywhere and borders opened and ferries connected the gaps. In reality, you cannot drive a full equatorial loop because oceans block the way, and some regions have no safe through routes. By plane, you can circle Earth in a day using a sequence of long-haul flights. The record attempts for circumnavigation show how tightly the schedule must be managed. The traveler is less a wanderer and more a package moving through a network. In orbit, you circle Earth every 90 minutes. This alone shows that the word travel can mean very different things. Another useful scale is the distance to the Sun. Earth is about 93 million miles from the Sun. That is called 1 astronomical unit. If a person flew at 500 miles per hour for 8 hours a day for 50 years, the total distance traveled would be around 73 million miles. That is close to 1 astronomical unit. So in one lifetime of heavy travel, you can rack up a sun distance of motion, even while staying on Earth. That is not because humans are fast. It is because lifetimes add up. But if you want to actually go 1 astronomical unit away from Earth, you must leave the planet. Only robotic probes have done that routinely. Space agencies send probes to the sun itself and out past the planets. They use rockets to escape Earth. Then they ride on their velocity. A human could in principle ride on such a trajectory, but the life support challenge grows. Space is not empty from the point of view of biology. There is vacuum, there is radiation, there are temperature swings, there is the slow wear of microgravity. So, the distance a human can travel in a lifetime is not only about the ability to get there, it is about the ability to stay alive while getting there. We can see this in the best data we have, which comes from astronauts. Astronauts on long missions lose bone density and muscle mass unless they exercise intensely. They deal with fluid shifts that change their faces and can affect vision. They face higher exposure to cosmic radiation. The International Space Station is shielded by Earth's magnetic field, and still the radiation is higher than on the ground. A trip to Mars would leave that protection. This means that even if we had the propulsion for quick Mars trips, humans would still have to solve the shielding problem. Shielding is heavy. Heavy is expensive in rockets. This is a recurring theme. The farther you want to go, the more mass you need to carry to keep the human alive. The more mass you carry, the harder it is to go fast. Now consider a person in a human lifetime who wants to go as far away from Earth as possible with plausible near-future tech. One candidate is a lunar mission, then perhaps a Mars mission. A lunar mission gives you 240,000 miles of displacement. A Mars mission gives you tens of millions. But it is not just the distance, it is time. A Mars mission might take 2 to 3 years of life, not counting training. A person could do that once. It is difficult to imagine a person doing multiple Mars trips in one lifetime, unless there is a large transport system and a safe station on Mars. So, for the next century, the maximum displacement by a human might still be measured in hundreds of millions of miles, not trillions. This places the human lifetime travel distance, in terms of displacement, firmly inside the solar system. But total path length can be far larger, because orbiting makes huge loops. There is a subtle point here. If you go to Mars, you do not just go in a straight line. You follow an orbit around the Sun. You might spiral or arc. If you include all that, the distance traveled by the spacecraft is larger than the simple separation between planets. Still, it is the same order of magnitude. The solar system is big, but it is still tiny compared to the distance to the nearest star. Now, to understand why interstellar travel is so hard, it helps to use another kind of comparison. We can compare energy per kilogram. To drive a car at highway speed, the energy to move 1 kilogram is small. To fly a plane, it is larger. To reach orbit, it is much larger. To reach a significant fraction of light speed, it becomes enormous. This is because kinetic energy scales with the square of speed in the non-relativistic case, and even more harshly near light speed. Double your speed, and you quadruple your energy. At light speed fractions, this is brutal. Now add the fact that rockets must carry fuel. The rocket equation tells you that to get a certain change in velocity, you need an exponential amount of fuel depending on your engine efficiency. This is why chemical rockets are limited. They have a certain exhaust speed. To get far beyond Earth, you need staging and huge fuel fractions. Nuclear engines could raise exhaust speed, reducing fuel needs. Fusion could do more. Antimatter, in theory, is the most energy-dense fuel, but producing it in large amounts is far beyond current ability. There are also ideas like beamed propulsion, where a laser pushes a sail. In that case, the vehicle does not carry fuel. The fuel is the energy source back home. This removes one limit, but creates another. You need huge lasers and precise aiming across long distances. Also, the sail must survive the beam. But if you want the maximum distance in one human lifetime in a realistic future scenario, beamed propulsion becomes interesting. A small probe could reach a fraction of light speed. A human ship would be harder, but the concept is in the same family. Now consider the human at the center. The human body can survive acceleration up to a point. Fighter pilots can handle high G for short periods with training and suits. But for long periods, even a few G would be too much. 1 G is normal. Half a G might be fine. 1/10 of a G might be fine. At those accelerations, you can build up speed over time. This means that if you can create a constant push, even if small, you can reach high speeds without a sudden shock. Ion engines are like this. They have low thrust, but can run for months or years. An ion-powered ship could slowly accelerate and reach high speeds over long times. But the power source must be large. Solar panels work close to the sun, but far out they produce less power. A nuclear reactor might be needed. Now, if we stay within the solar system, even modest speeds can make a big difference. A ship that can go 2 or 3 times faster than current probes could reach the outer planets in a human lifetime. A ship that can go 10 times faster could make the outer solar system a place of years, not decades. So one plausible answer to how far a human could travel in a lifetime is this. With improved propulsion and life support, a person could visit the moon, Mars, perhaps an asteroid, perhaps even the moons of Jupiter within a lifetime. But the jump from there to the stars is huge. Now there is another way around the biological limit. You can slow the body. If you place a person in a deep sleep state for years, or in a suspended animation-like state, you could stretch their lifetime clock. They would still age less during the trip. This is speculative. It is not available today. But even without it, there is another trick. Time dilation does the slowing for you if you go fast enough. But we already saw the cost in energy. So the maximum lifetime travel distance depends on which trick you allow. If you allow none, then the limit is solar system scale. If you allow time dilation with near light speed, the distance can become galactic scale. To make this less abstract, imagine a ship that could reach 90% of light speed. At 90%, the time dilation factor is about 2.3. That means that for every year on the ship, about 2.3 years pass outside. If the ship traveled for 20 years of ship time, it would cover 18 light years of distance, and about 46 years would pass outside. That is still within a human lifetime on Earth. The traveler could return and still find some of their peers alive, but the engineering is still extreme. Now imagine 99%. Now 20 years of ship time would correspond to about 140 years outside. That is beyond the normal human span. So at higher speeds, you stop having round trips. The travel becomes one way. This is another human limit. A person is not only a body. A person is a network of relationships. If you travel so fast that centuries pass outside, you are not going to visit. You are going to vanish. So, even if physics allows it, the definition of travel changes. Now let us return to Earth and look at the most extreme, plausible lifetime travel in total distance. If you want to maximize total miles with existing tech, you can either stay in orbit or you can stay in the air. Orbit is not currently available to most people. Air travel is. So imagine a person who becomes a flight crew member at age 22 and stays until age 65. That is 43 years. Suppose they fly 800 hours per year, which is near the high end for pilots due to regulations. At 500 miles per hour average, that is 400,000 miles per year. Over 43 years, it is 17 million miles. That is about 680 times around Earth. If a person could fly more hours, perhaps as a passenger without regulations, the total could rise. But the body is still the limit. Pressurization cycles, sleep disruption, exposure to higher radiation at altitude all add costs. It is possible for some people to live that way, but it is not easy. Now compare that to a person who spends time on a space station. 1 year in low Earth orbit can be over 140 million miles of path length. Even a few months is tens of millions. So if a person could spend, say, 5 years total in orbit across missions, their total miles could exceed 500 million. That is 2,000 times around Earth. Again, this is distance without displacement. The human has not gone far away, but they have moved far. This reveals a funny truth about distance. If you want to travel far in terms of path length, you want to move in circles very fast. If you want to travel far in terms of displacement, you want a straight line away from home. Now, the question most people mean is displacement. They want to know how far from Earth a human could get. So let us focus on that for the final stretch. A human lifetime is maybe 80 years. If you allow a person to launch at age 35 and return by age 55, you have about 20 years for the mission itself, plus training. In 20 years, what displacement could you reach with plausible propulsion? With a chemical rocket, you could reach Mars and return well within that time. You could reach the asteroid belt and return. You might reach Jupiter with a fast trajectory and perhaps return, but the radiation and time make it hard. With nuclear thermal propulsion, you could reach Mars faster. You could perhaps reach the outer planets in less than a decade. With nuclear electric propulsion and continuous thrust, you might reach high speeds over time and cut travel time. With fusion propulsion, if it ever becomes practical, you could reach the outer solar system quickly and perhaps reach the heliopause, the boundary where the sun's solar wind gives way to interstellar space. The heliopause is roughly 120 astronomical units away, depending on direction and solar activity. 1 astronomical unit is 93 million miles, so 120 is about 11 billion miles. Voyager 1 took more than 40 years to reach that region. In a human lifetime, a fast ship could do it. That would be a meaningful milestone. A human could leave the solar system, not just leave Earth. But even then, the nearest star is still 25 trillion miles away. Leaving the solar system does not make you close to another star. It only means you have stepped out of the sun's neighborhood. This shows why the phrase interstellar is misleading. The space between stars is not a short bridge. It is an ocean. Now imagine the most optimistic future ship that still respects known physics and does not rely on magic. Perhaps it uses fusion, perhaps it uses a laser sail, perhaps it uses a powerful reactor and a high exhaust speed engine. Suppose it can reach 10% of light speed. 10% is about 18,600 miles per second. At that speed, you cover 1 light year in 10 years. Alpha Centauri is 4.3 light years, so it would take 43 years. That is close to 1 lifetime. But that assumes you can accelerate and decelerate quickly, and that you can protect the ship from dust impacts. It also assumes you can keep a human alive for decades in a closed system. This is still hard, but it is a target that fits the question. So, a reasonable upper bound for displacement in 1 human lifetime, if we imagine a far future but not impossible ship, might be a few light years. That would let a person reach the nearest star. If we push further, allowing higher fractions of light speed and accepting time dilation and one-way travel, then the distance can grow. But the human story changes. Now, there is a last point that often gets missed. Distance is not only how far you can go, it is also how far you can return from. A person can travel far in one direction, but the ability to come home is a different measure. On Earth, return is easy because the environment supports you. In space, return requires fuel, planning, and timing. On interstellar journeys, return might be impossible. So, when we ask how far a human could travel, we should ask whether we mean a trip or an exile. A trip implies a return. An exile is one way. Now, in 1 human lifetime, a person could certainly travel one way very far if they do not care about return. and they are willing to die at the destination. They could take a fast trajectory past the outer planets and keep going like a human voyager. They might cross the heliopause and then the Oort cloud region if they lived long enough. The Oort cloud, if it exists as a dense cloud, may extend tens of thousands of astronomical units from the Sun. That is a huge distance. At 100 astronomical units per year, it still takes centuries. So even the outer edge of our own system is beyond a single life unless you go very fast. And that brings us back to the core truth. A human lifetime is the wrong scale for the universe. The universe was not built to fit our years, but our tools can stretch what a lifetime contains. In the last few hundred years, a person went from spending most of their life within a few miles of home to being able to cross the planet in a day. That is a change so large it is hard to feel. If you take a child born today and imagine the world at the end of their life, you are imagining 50 or 60 years of innovation. That could be more transformative than any math we can do now. So, the farthest a human could travel in a lifetime is not only about the physics, it is about the era. If a person lives during the first century of routine space travel, their maximum displacement could jump from thousands of miles to millions. If they live during the first century of advanced propulsion, it could jump again. But even then, the stars will still be far. So perhaps the most honest answer is a range. In an ordinary modern life, a person might travel a few 100,000 miles total, mostly in loops, mostly near home. In a travel-heavy modern life, a person might reach a few million. In an extreme career in aviation, perhaps tens of millions. In a career that includes long stays in orbit, perhaps hundreds of millions or more in path length. In a future with routine missions to Mars and beyond, perhaps hundreds of millions of miles of displacement. In a far future with 10% light speed travel, perhaps a few light years of displacement. And in the most extreme case, with near light speed and time dilation, the distance could be thousands of light years in one lifetime of ship time, at the cost of leaving your own era behind. All of these answers can be true, depending on what you mean. And maybe that is the final lesson. Travel is not a single number. It is a choice about what you value. Do you value seeing many places on Earth, even if you never leave it? Do you value leaving the planet, even if you never come back? Do you value returning, even if it means going slower? Do you value staying in your own time? Or do you value distance so much that you are willing to let the rest of the world age away? A lifetime is made of moments, not miles. Miles are only the trace that motion leaves behind. And when you think about distance at the scale of light years, it becomes clear that the deepest travel a human can do is not only across space, but across the limits of what a human can build. The question will stay open as long as we keep building. Even if the limit stays out of reach, the attempt changes what a lifetime can contain, and it changes what distances feel like to the human mind. There will always be a farther shore. This was a quiet archive story, where the story ends, sleep begins,